Astronomy Department and the STEM Club, I'd like to welcome Dr. Geoffrey Lovelace to SCC. Dr. Lovelace is an assistant professor of physics at Cal State Fullerton. He got his bachelor's degree from the University of Oklahoma in 2002. Afterwards, he did his graduate studies at Caltech, and then he got his PhD from Caltech in physics in 2007. Dr. Lovelace is currently working on gravitational wave research, which he'll tell you more about today. It's really cutting edge stuff, very exciting stuff, actually. So just a fun fact. You guys all know Stephen Hawking, right? Very famous physicist, guy in the wheelchair, funny voice, right? He has a really good friend named Kip Thorne. Now, Kip Thorne is also a very good physicist, very famous in the physics field, extremely well known. Now, Kip Thorne and Stephen Hawking once had a bet on the existence of black holes. And eventually, Kip Thorne won this bet, and in return, Stephen Hawking had to buy him a year supply of Penthouse magazine. So, why am I telling you this? Because Dr. Lovelace is Kip Thorne's student. Kip Thorne was his PhD advisor back in Caltech. And also another exciting fact, in November of this year, Kip Thorne, actually he's working with the Nolan brothers on a movie in Hollywood. And in November 4th, I think, it will be released, and it's called Interstellar. So, watch that. Matter tech. You guys can please help me give a warm welcome to Dr. Lovelace.
Well, thank you all for coming. Thank you very much for the invitation. I'm really glad to be here. I want to tell you a little bit about a couple of things. I'm going to start out by talking a little bit about some of the work that I've been doing with some of my students, including Haroon. And I'll talk a little bit also about traveling through time, even though it's a little bit outside of what I normally work on. Haroon was telling me that this was by popular demand, so I'll talk a little bit about that too. Okay, I want to start out by just saying a little bit about the group that I work in at Cal State Fullerton. So I'm in the new Gravitational-Wave Physics and Astronomy Center at Cal State Fullerton. So this is a research center led by 3 professors there. I'm one of them, and I'll tell you a little bit more about black holes smashing into each other, which is what our group works on. Jocelyn Reed is another professor there, and she and her students work on studying neutron stars, which are, I won't say too much about this talk. They're the result of, there were some stars that are not quite big enough to turn into black holes. When they die, they turn into neutron stars, these really, really small but dense stars. And then Josh Smith works on a gravitational wave experiment. So during the talk, I'm going to say a little bit about gravitational waves and what they are and why they're interesting, and what we hope to learn about the universe from them. Let me say just a little bit about myself. So one thing that you should know is that I have an identical twin brother. I'll let you guess which one of these people is me. Maybe it's obvious, maybe it isn't. But the important thing for this talk is that when we were kids growing up, we played a lot of video games. One of those video games was this one here, where I fell into a black hole. That's where I heard of them for the first time. And I thought they were so cool, I started reading about them. And then when I was in high school, my mom was the director of a community college library near where I grew up in Pennsylvania, and she brought me this book. If you want to know a little bit more about what's going on, this is a really great book. It's got great pictures, it doesn't have too many equations in it or anything. But when I started reading this, it really started dawning on me that you could work on black holes for a living. So I was like, all right, this is what I'm going to try. So there are 2 morals to this story. One is that reading books from the library is good for your career, and the other is that playing Nintendo games is good for your career. Okay, so what I'm going to talk about today, I'm going to start out by telling you a little bit about the work that Haroon and the other students that I are working on at Cal State Fullerton at the Gravitational-Wave Center. I'll talk about gravitational waves and black holes, and then I'll talk specifically about black holes smashing into each other. And when I'm finished with that, then I'll talk about time travel and 2 different kinds of time travel, going forwards in time and going backwards in time, and what we think the laws of physics have to say about that. It turns out that the laws of physics that are relevant are very, very much related for all of these topics. Okay, so why is there so much excitement in gravitational waves? Well, I wanted to start out by showing you just this picture. Some of you might have seen on the front page of the New York Times back in March, there was an announcement about some scientists finding ripples in space and time. This was an experiment that, for the first time, was detecting the echo of gravitational waves from the beginning of the universe. This experiment's still awaiting confirmation, but this is just one thing that we're very excited about, that we're going to start being able to look at the sky with this new kind of wave, and I'll say more about what gravitational waves are in a bit. But I wanted to show you another example of how gravitational waves are starting to show up in the media.
I gotta tell you, the more I read about the primordial gravity wave discovery, the more excited I get.
I know, being an astrophysicist right now is like being a rock star.
Okay, so I don't know about being a rock star, but I'll try to turn the talk up to 11. We'll see how it goes. But I want to tell you why they're so excited. Okay, so they're excited about all the science nerdy stuff on the Big Bang Theory, but why specifically gravitational waves? Well, to answer that question, before I can tell you about gravitational waves, I need to say a little bit about gravity. So let me tell you a little bit about how gravity works. So the theory of gravity that you'll learn if you take an introductory physics course here is Newton's law of gravity. The idea is that anything that has mass, any two objects that have mass will attract each other, and the force of that attraction is what you think of as gravity. This theory is very old, but that doesn't make it any less relevant. In almost every circumstance, this is great. In almost every circumstance in everyday life, this theory works just fine. But in this talk, we're going to be talking about things that are a little bit outside of where Newton's law works. It works when gravity isn't too strong and when things aren't moving too fast compared to the speed of light. And we're going to break both of those assumptions, and so we need another theory of gravity. It's not that Newton's theory is wrong, it's a really great approximation in everyday life, but not so great an approximation for the extreme kinds of situations we're going to be looking at. So about 100 years ago, Einstein came up with a different way to look at gravity, general relativity. So in general relativity, gravity isn't thought of as a force that's pulling things around. It's thought of as curved space and time. So mass curves space and time. The more mass you have, the more curved it gets. And then that curvature affects how mass moves through the universe. So I have a little movie here I want to show you. This is Brian Greene, and he's going to visualize space-time as a pool table. Now, if you put a mass on the pool table, then it curves the geometry of the table. If the geometry were flat, when you hit the cue ball, it goes in a straight line. Because it's curved, it still tries to go in a straight line, but the straightest possible line it can go in is actually a circle. And that's how I want you to picture the effect of curved space and time. And this is exactly what happens when the moon goes around the Earth. The Earth is curving the space and time around it, and the moon is trying to move in a straight line, but because the geometry is curved, it just keeps going around in a circle. Okay, now, we're going to be talking about black holes, so I have another visualization I want to show you. Have any of you ever seen one of these coin funnels before? Have you lost any money to one of these things? So it's going into slow motion here, but again, this is a visualization where it gets more curved as you get closer. But there's a difference. The penny is falling in, but the moon doesn't fall into the Earth. So can any of you think of what's a difference between these two movies? Yeah.
Okay, so the black hole's like an abyss, while the Earth, there's no abyss.
Right. But what causes this to be an abyss? What causes the penny to fall in? It's losing. No, that's on the right track. It's friction. You hear some sound and some air resistance that causes the penny to lose energy as it falls in. This is also a lot like a black hole, like you said, because it's an abyss. A black hole is a region of space-time where if you fall inside, you're not coming back. And similarly, when you hear that clink, the coin has crossed the coin horizon and it's not coming back. So that's a great way to think about black holes. So what's a black hole? It's a region of curved space and time where gravity is so strong that nothing can get out because light can't get out. And if light can't escape, then you can't escape either because it's impossible to travel faster than light. Now somewhere inside the black hole is something called a singularity where gravity is infinitely strong. So it's even worse news. Not only are you never coming back, but gravity is going to become infinitely strong and rip you to shreds. So it's not good for your health. It's very bad to travel through the black hole. Black holes are formed when massive stars die, but they're a lot like that coin funnel. Just like the coin isn't coming back, if you fall into a black hole, you're not coming back either.
Now I want to show you what a black hole looks like. Here's a black hole. This is the surface, the horizon, where if you fall inside, you can't ever get out. It's just a sphere. But it's hard to visualize curved space-time in 3 dimensions. So 4 if you count time. So what I want to do here is I'm just going to take a cut and just look at the equator of this black hole. So now I only need 2 dimensions to describe the space of the black hole, and I'm going to use that third one to show how it's curved. And that gives you a diagram that looks an awful lot like that coin funnel. Now, what you have to imagine is that if you're near the black hole in the plane defined by this red line, then you move around through space and time like this. And this curvature gets stronger and stronger as you get closer to the horizon, and so gravity would pull on you stronger and stronger as you get closer. So, but on the other hand, just like that coin could go around in a circle, black holes don't suck everything in automatically. Just like a coin could swirl around here, if you could also get in a spaceship and just orbit above a black hole and be fine and not just get sucked right in. So picture gravity the same way. Just like the coin gradually, if there's something to cause it to lose energy, it can spiral in, but it just can also orbit around like this. The stronger the curvature, the stronger the gravity. And the curvature gets bigger, the more mass you have. So that brings a question of, how big are black holes? Well, in terms of how massive they are, they're actually really huge. Black holes come in 2 flavors in the universe. One kind is about 3 to 30 times as massive as the sun. But there's another kind of black hole that we think is in the center of most galaxies that's at least 1 million times as massive as the sun. It could be more massive, it could be less massive. Okay, so how big is this? Well, it's a lot of mass, but these things really aren't very big. Let me show you. Here is Cal State Fullerton, where my office is. And here's the 55, where I was driving down this way. So we're somewhere in here. Now, suppose Haroon was working on a computer simulation and something went horribly wrong, and suddenly there appeared a 10 solar mass black hole 10 times the mass of the sun, centered on my office. How big would that be? Well, this is how big it would be. So it doesn't even reach to downtown LA. It'd be bad news for us, shortly bad news for downtown LA, but the surface of the black hole is only this big. So this is really small. 10 times the mass of the sun compressed to less than the size of a city. That's how small black holes are. If the Earth were a black hole, this is how big it would be. I understand there was a bit of a bribe for some of you to show up today, some extra credit. This would look really awesome in a summary of what's happened, of what the talk was about. Black holes, the mass of the Earth is smaller than a golf ball. So imagine compressing the whole Earth to be that small. That's how dense these black holes really are. So they're very, very extreme objects. They're some of the most extreme objects anywhere in the universe. Black holes have a couple other properties that are going to be important for us. They can rotate. Just like a tornado can swirl the air around it, a black hole can cause the space and time around it to get swirled around. So if you tried to dive in head on, you could get, if the black hole is rotating, it will actually pull you into rotation around it. You won't be going in a straight line anymore. They actually will pull things around them in rotation. One other property I wanted to mention is going to come up in the second half of the talk, which is time. So as you get closer to a black hole, it turns out that time flows more slowly. So the color on this graph is showing how fast time is going. So out here, time is going the same rate as it would be very far away. As you get closer and closer to the horizon, time starts flowing slower and slower, as seen by someone from outside. So if I were to send Haroon down towards the black hole, and he were going to orbit around here, I wouldn't want to ask him to go all the way into the black hole, then his clock would tick slower than mine.
So just my question, is the center of the black hole solid?
That's a great question. Is the center of the black hole solid? I'm not quite sure how you would define the black hole center. Inside the black hole is a singularity. I don't know that you would say it's the center, but it's the point that everything goes to. And it's an end of time. Just like this table has an edge, and there's no more table off the edge, there's no more time and no more space past the edge of the space-time inside the black hole. And that's the center. So I think that's, but I don't know how I would call that the center. Yes?
So as time gets slower, as you go closer to the bottom, would it just stop at the very bottom?
Well, from your point of view, I have another student named Evan that I like to use to demonstrate this. I mean, I've got to stay safely away from the black hole because I have to write all the papers out and everything. But if I were to send Evan to dive into the black hole, From his point of view, time just flows normally. But from my point of view, I would see his time tick slower and slower and slower as he approaches the horizon. And eventually, from my point of view, it would slow so much that if he were, say, sending me a pulse of light every second, according to him, I might have to wait 100 years or 1,000 years or the age of the universe to get the next pulse. But from his point of view, he wouldn't see anything unusual. Yes.
Because it can't actually go inside the black hole, how do we know that it's going slower down inside of it? How do you explain that then?
Well, that's a really great question. We can go inside a black hole, but we can't come back and tell anyone what we find. So how do you know what's happening? Well, the only way we can know what's happening inside is to see what the laws of physics predict. This is actually a very open question. The laws of physics, people are still doing computer simulations now to try to figure out what the laws say must happen inside a black hole. And we're not really sure yet, but there are some people working on it. Yeah.
So can like anything actually like get truly like I guess sucked into a black hole if time reaches like such a slowdown?
Yes. So I would say things could fall in. Black holes don't really suck. So I like to tell my students black holes don't suck. But just like an object, a meteor could fall to the Earth. A meteor could fall into a black hole, or you could if you weren't careful. You could fall into it. But it's just like falling down to the Earth, except there's no surface for you to bump into. Instead, the surface would be the horizon. Now, the time slowing down, this is a weird thing about how time works. It only slows down from, so if I'm staying out here at a safe distance, and I'm going to send one of my students down into the black hole, from my point of view, I would see the student's clock tick slower and slower and slower. But what the student would experience would be nothing out of the ordinary as they fall inside the black hole. It's just gradually the gravitational force would get stronger until eventually it was strong enough that it would rip them up and kill them. But just the fact that they fell inside the horizon, their time doesn't stop from their local point of view. It's just that it's ticking much slower than my time is. Yes?
Since they're so massive, do you fall faster?
Since there's, with a more massive black hole, then yeah, the curvature is stronger. So if you were going straight in, you'd fall in faster. Yes?
If you were to send a pulse to your student, what would it appear? How would it look to them?
Yeah, how would that look? So that's a really good question. So I think the pulse would look bluer from the student's point of view. It would look like, because he would think my time was flowing faster. But yeah, I don't think about that point of view as much. But yeah, if he were watching me, he would see my pulses coming at some different rate than if there were no gravity there. Yes.
Does that have anything to do with just the relativity of time?
Yes, this has everything to do with the relativity of time. And I'll talk more about that in the time travel section. But basically, different observers don't agree on how fast time is flowing. That's the key on how this works. My student falling into the black hole and I don't have to agree on how fast time is flowing. That's why I think his time is stopped, but he doesn't agree. And so that's a great point, because that's exactly what's going on here. Yes?
So what is the top part of the black hole?
So this is a region farther away, and the curvature is getting smaller and smaller. And if I were to continue this graph to show infinitely far away, it would just be flat. And so out here is just the outside universe. It's everything else outside, far away from the black hole.
So if something were to cross over the top of that, I guess we could call it the black hole, would be, if you crossed over the top of it, would you fall in?
No, so not necessarily. Just like the moon goes around the Earth, you can picture the gravity of the Earth as looking a lot like this, except it's not as steep. It doesn't go as far down. There's no horizon at the bottom. The Earth's surface would cut this diagram off at some place. But otherwise, it works the same way. Just like in that movie, the moon was going around and around in a circle around the Earth. Similarly, if you came into the diagram up here, you could go around the black hole in an orbit and be fine. Just orbit it in a circle. You wouldn't necessarily fall in.
So a person couldn't really, if the Earth turned into a black hole, no one would fall in it because it's too small.
Okay, so if the Earth turned into a black hole, actually the gravitational force on us would be the same, because it turns out the gravitational force outside a black hole is the same as the gravitational force outside any sphere. The only problem is there wouldn't be any ground for us anymore, and so we would start falling towards the black hole horizon. But it's too small for all of us to fall in, so then weird things would happen where if the black hole is only this big, it could maybe go right through you like a big bullet or something. So still probably not good for you, but yeah, some black holes that small would you would have to be compressed in order to fall all the way into it. Well, these are all really great questions. I think what I want to do is take a few more questions a little bit later, but I want to make sure I have time to get through the talk. So I think I want to go on for a bit, but I'd be happy to answer more questions at the end or a little bit later. Yes.
So
That totally didn't
if a black hole just fell on a planet, would it just go down towards the other side of the planet, then back up and down, like a ping pong
Yes.
like a paddle ball?
Yes, it turns out that if you look at what Newton's law of gravity says happens if you were inside the Earth, and you can imagine you can either travel through the Earth or you have a little hole drilled all the way through the Earth, then the equation that Newton's law of gravity turns into is actually Hooke's law for mass on a spring. And so the black hole, if you just released a black hole from rest right at the surface of the Earth, a little one, then what Newton's law of gravity says would happen is it would just go back and forth like a mass on a spring.
So it would just devour the planet very slowly then?
Well, I think it would just punch a little hole and go back and forth through it, if it were released from rest. But if it hit the Earth with some initial speed, it could just go right through it. Now, I should say, black holes this small, we're pretty sure don't exist. We don't know of a way that the universe can actually produce them naturally. Yeah.
So since black holes would be the center of a galaxy,
Yes.
is our entire galaxy, all the solar system, and it going towards the black hole that's towards the center of our?
That's a great question. There is a black hole at the center of our galaxy, and we are not moving to it. Just like in the movie, the moon was orbiting the Earth without actually falling down onto it. The solar system orbits the center of the galaxy without actually falling into it. So it's the same basic idea. Okay. I didn't see any questions. I'm going to take an opportunity to go on and tell you about the next thing I want to talk about, the black holes smashing into each other. So here's a picture now where these funnels are representing the curved space-time in the equator of two black holes. And they're going to orbit around each other. And what happens is they spiral around each other. But just like that penny lost energy to friction that caused it to fall in, the black holes lose energy and spiral together and move faster and faster until they smash into each other. So here's the beginning. Here they're getting closer together. And here they've merged into some really strange, distorted black hole. The picture I showed you before had the surface of the black hole nice and spherical. But this black hole would look more like a dumbbell. It's a really strange shape, but it doesn't stay that way for long. Just like if you strike a bell and deform the metal and give it some weird shape, the bell is going to ring, but that ringing is going to die away. And it turns out black holes behave exactly the same way. Anybody in physics class might have seen the equation for a damped harmonic oscillator. That's the equation of this black hole. It rings, but the ringing dies away. Now what happens here? Why do the black holes lose energy? Why do they fall together? Well, it turns out they're converting part of their mass into waves of gravity. These are the gravitational waves that I was talking about earlier. So what does that look like? If you were to zoom out from this picture, so the black holes are just these little dots here. What you're seeing is little ripples of curved space and time. So instead of a funnel shape, the curvature is more like little ripples. These are just like water ripples that go on a pond. If I throw a rock in a pond, little water ripples travel out and travel across the pond. And if you're clever enough, you can measure those ripples and learn something about what the rock was like that fell in. And similarly, although these gravitational waves travel a lot faster than water ripples, they travel at the speed of light, you can try to learn about the black holes and how they interacted as they smashed together by looking at these ripples of gravity. Yeah.
What processes or reasoning do you use to deduce that this would actually happen?
What process of reasoning do you use to deduce that the black holes would lose energy and fall together?
That they would actually behave in this way when they hit each other.
Yeah.
We haven't observed it.
Yeah, so how do you know that black holes actually do this? They're black, you can't actually see it happen. What makes us think that anything like this actually happens in the universe? That's a really great question. So we have a theory that describes gravity, relativity, which describes gravity as curved space and time. So far, we haven't found experimental evidence that contradicts this theory. So as far as we know, it's true. And one of the consequences, if you solve the equations that describe the theory mathematically, say on a computer, is that black holes will do this when they get too close to each other. Whether this really happens or not, though, well, we're pretty sure the theory is right. We've never found an experiment that contradicted it, but who knows? So what we really want to do is we want to measure these waves of gravity so that we can actually find out more directly do we actually see these? If we see gravitational waves like this and they have a certain imprint, they sound a certain way, we can say, oh, we recognize that sound. That sounds like two black holes smashing together. And so actually, this whole idea of gravitational waves is to try to firm up our understanding experimentally that this really happens. So far, this is just what the theory predicts, but it's the best theory we have at the moment. But that's a really, really insightful question. That's getting at the heart of why we want to look at these things. Merging black holes are the most violent events anywhere in the universe. They can convert something like twice the mass of the sun into pure energy. This is a huge amount of energy, but it's totally invisible when they smash together. If there's no gas nearby or something to heat up and be disturbed, you can't see this with light. You can only see this with waves of gravity. So we would like to do some astronomy with a new kind of wave, not just light, but with gravitational waves, so that we can look at things like colliding black holes and see, does this really happen? Is the theory really true under these extreme, bizarre circumstances? Let me show you another picture of gravitational waves, and I'll talk about how we try to see them. So what are gravitational waves? What would happen if a gravitational wave came by? Suppose a gravitational wave were going straight into the screen. Then what would happen is, if you had a ring of particles that were just sitting there and weren't moving at all, then as the gravitational wave comes by, it stretches and squeezes the space and time around it. And that causes this kind of stretching and squeezing motion that you see here. Now this is just one ring of particles. Suppose I had a whole cylinder of them and gravitational waves were passing through that. This is what it would do. So these particles would normally not be moving, they'd just be sitting there. Imagine you just set up a cylinder like this on the space station or something, and just floating. If a gravitational wave came by, it would cause them to stretch and squeeze like this in some wave patterns. The gravitational wave would fly. The gravitational wave would travel at the speed of light. So these waves are a lot like light, except they're not made of electricity and magnetism, they're made of gravity. Everything we know about the universe beyond the solar system so far has come from light. But we want to start looking at waves of gravity, the ripples of curved space and time that have this effect on matter when they come by, to try to see things in the universe that you just can't see with light, like colliding black holes. Okay, so how can you actually see them? So here's that cartoon of ripples of warp space and time. By the time they get to the Earth, they'll actually travel right through the Earth. Pretty much everything in the universe is transparent to gravitational waves. But as they go through, they would cause a little ring of particles to stretch and squeeze. Now, building a ring of particles is expensive, so we've actually only built two. We built one at the top and one at the right corner. And what we did is we put a mirror right here, and a mirror here, and another mirror way down there. This tube is 2.5 miles long. This is a vacuum tube. It's 2.5 miles long. That was kind of expensive for them to build. What they did, they actually built a few of them, because LIGO wanted me to build a few. And when the gravitational wave comes by, it will cause those mirrors to wiggle by stretching and squeezing the space, just like it caused that ring of particles to stretch and squeeze on the video I was just showing. The difference is that the stretching and squeezing is way, way exaggerated in that movie. If I showed how much they actually move, you'd never see it in the movie. How much smaller? Well, these arms are 4 kilometers long, 2.5 miles. They will stretch and squeeze the space between them by less than the size of a proton, by 10 to the minus 18 meters. So how small is that? So we're all, to the nearest factor of power of 10, 1 meter tall. About a meter. Divide that by 10,000, that's how thick a single little strand of hair on your head is. If you go down another 100 below that, that's how far it is between the peaks of light waves that are going by. Go down another 10,000, and now you're at the size of an atom. You go down another 100,000, and that's the size of the nucleus of an atom. And another 1,000 times smaller than that. That's how little these mirrors are going to wiggle when a gravitational wave comes by from the strongest sources in the universe that we know of. The reason it's so weak is because these things happen so far away. Just like stars that are very far away are dimmer than if they were right next to us. When black holes smash into each other millions of light years away, by the time the waves get to us, they're really weak. And so the brightest waves that we realistically expect to see will only move these mirrors a little. So I'm only a theorist, so I just say we measure this using lasers. It's actually a real experimental tour de force how we're going to be able to do this. This experiment is called the Laser Interferometer Gravitational Wave Observatory. It's called LIGO. And it's going to start looking for gravitational waves within the next year. And we expect, once it's fully operational, to see something like 10 waves from sources like colliding black holes or exploding stars, or things like that, every year. We expect to see something like 10 of these waves every year, maybe more. So we want to see these waves so that we can go back and find out, is this theory of gravity true? Yeah.
Compared to the speed of light, how fast do gravitational waves move?
Gravitational waves move at exactly the speed of light. It turns out any particle that has no mass will travel at the speed of light. And light is carried by particles called photons that have no mass. Gravitational waves are carried by particles called gravitons. But that's a little bit outside of the scope of the talk, but it turns out they travel at exactly the speed of light. Okay, so you can imagine this is a dicey, very delicate experiment. You can imagine this is a delicate experiment. We're trying to make this little tiny wiggle. So here's a picture of what your readout from this LIGO experiment might look like. Here's a gravitational wave, but it's hidden inside some noise. So what would that look like? I've got a sound to play for you, and you might or might not be able to hear it, but about 5 seconds in, there's a little click that's a gravitational wave that's hidden inside the noise. Yeah, it's really hard to hear them inside the noise. So what do we need to do? We need to predict as accurately as we can what those waves are going to look like. Just like if you're in a crowded room and you hear somebody calling your name, it's easier to pull that out than just all the noise that's going on. Or if you've got a car radio and you've got really lousy reception and a lot of static, if you know the station you're tuned to just plays the same 3 songs over and over and over, it's easier to tell if they're there or if you're just getting nothing because you know what you're listening to. And so this motivates the work that a lot of research groups, including mine, are doing. We're trying to predict what the gravitational waves will look like from colliding black holes. So we're trying to see very precisely, what does the theory say will happen? It says that the black holes will spiral together and merge and emit some gravitational wave. We're trying to compute how that works. It turns out the equations are too hard for anyone to solve. No one knows how to solve them except using big computers. So I want to show you a little bit of a movie about this. My research group is part of a big collaboration between Cal State Fullerton and some other places, Caltech and Cornell. And what we're all trying to do is we're trying to predict what the gravitational waves look like when black holes smash into each other. But different black holes that are different sizes or spinning about different axes will behave very differently. Now, Haroon spent last summer and then into the fall rendering a movie of a few of the different simulations, and I'm going to play that for you. The circles are the horizons. These are the surfaces where if you fall inside, it's bad news for you. And they're tracing out their orbits. Now, these different black holes are set up in different ways, and they behave differently. Some of them orbit each other just in a disk. Some have really complicated orbits. And they're timed so that it's going to pause just before they merge, all at the same time. So now they're about to create new black holes. And there they are. And we're trying to simulate all of these different kinds of cases so we can predict what the gravitational waves would sound like. These are really expensive. This is a computer. That's a Cal State Fullerton. On this computer, just one of these simulations might take something like 50 days. On my laptop, it might take years to do just one of them. We want to do thousands of them because we want to predict all the different kinds of black holes that might be out there and see what Einstein's theory tells us about precisely how they'll behave when they smash into each other. We need to do that so we can tell the gravitational wave experiment what they're looking for so that they have the best chance to see as many as they can. Here are just a couple more movies. Here are 2 black holes. This is a movie by Evan, the student I like to drop into black holes for science that I mentioned earlier. And here I'm going to pause, zoom in, and you're going to see the black hole surfaces get stretched around and then they merge into some black hole that then relaxes to some nice simple shape. And the movie's going to speed up again a little bit. Here's another one. This time, one black hole is much bigger than the other. I'm tracing out their orbits, and these are their horizons. And watch what happens. It's going to go around one more time. And now the little black hole is going to smash into the big one, and it becomes one. These emit slightly different sounding waves of gravity. Now, this isn't just an artist's picture. This is the result of computer simulation solving Einstein's theory of relativity to see what would happen. Let me play for you a sound really quick. The sound is connected to how the black holes move. So for this particular simulation, I'm going to show the black holes moving around, and you can listen to what the gravitational wave would sound like, except I've slowed it down by 4 times so you actually have time to hear. Sound. That's what the gravitational waves sound like for merging black holes. It turns out they merge at frequencies we can hear. So if you were to plug your gravitational wave detector into your headphones, that's what you would hear for that particular case. But it'll sound slightly different for different kinds of black holes. Now, I want to show you another movie. This is a movie that's going to lead into the second part of the talk part about time travel. Once again, so at the top I'm showing the two black holes' horizons. This time they're just colored black, and they're tracing out their orbits. The bottom is showing the gravitational wave, if you were to put the sound on a screen, like if you ever connect a microphone to a screen. The middle is showing the curvature of space, and the color is how much time slows down as seen by someone far away. And so here I'm going to pause when they merge, and you have this really strangely shaped black hole, but then it rings like a bell and relaxes down to a final big black hole. So this is a case where what would happen, suppose you survived outside the horizon, you didn't fall in, but you were down here in this yellow region. Time for you would look like it was flowing slower, according to someone who's far away. And that leads into the next part of the talk about time travel. Time flows at different rates, depending on how close you are to some massive object and some other things. And you can try to imagine exploiting this and say, could you exploit this to travel through time? So that's what I want to talk about in the second part of the talk. So there are two different kinds of time travel. One kind is traveling to the future. So if you've seen this movie, here are the flying cars that there's no way we're going to have anytime soon. I don't know what else they did here. But this is supposed to be next year. That makes me feel old. But this is supposed to be 2015 next year. It's supposed to be October 21st next year. Okay, fine. So traveling, you can travel in time to the future, or you could also imagine traveling in time to the past. And that was a different Back to the Future movie. Now, there's a big difference. You're going to get to the future eventually, assuming you survive that long. So you can imagine that it's easier to travel to the future than the past. And that's going to turn out to be true. That's what I want to talk about for the rest of the talk. And then I'd love to answer any more questions you might have. So I'm going to talk about forward time travel first. The strategy here is you can exploit things like what we were talking about. If there were a handy black hole nearby, what you could do is you could fly on a spaceship down nearby, and then everyone else back on Earth would see your clock ticking slower, because objects' clocks tick slower when they get closer to massive objects, like black holes. Anytime you get near anything that's got a lot of mass, your clock will tick slower than the clocks far away. But also, relativity says that if you're moving faster, your clock will tend to tick slower. So if I were to stay home and my brother were to get on a rocket and fly out into space at some very high speed, his clock would tick slower than mine would. And we can exploit both of those effects to try to slow down your rate of time compared to everyone else on Earth. So, for instance, I might experience 1 second, and the Earth maybe experiences a year or 100 years. That's future time travel. All you have to do to travel to the future is get your time to flow a lot slower than everyone else's. And then when you're done, you're in the future. So yay for you. So it turns out you might not know this, but we've actually done this. So these scientists here, I don't know how to say this name, Hackbell and Keating, in 1971, what they decided to do was to fly really fast around the world. And they put an atomic clock, which looked like this back then. They took an atomic clock with them and they put it on a plane. And this is already looking a little dated because the airline that they flew on doesn't exist anymore. Anyway, they decided they were going to compare this clock, which is really, really precise, way more precise than any watch you might have. And they're going to compare this clock that's on the plane with the clock on the ground. And they're going to try to see if they can travel into the future by causing their time to flow more slowly. So how does this work? So here's a cartoon of what the theory of relativity predicts when you do this. Here's a clock on the ground. This is everyone back on Earth and not in the plane, the time machine plane, the wannabe time machine. Okay, so the clock on Earth is going to tick at a certain rate. Now relativity predicts that because the plane is moving much faster than the ground clock. Okay, I'm going out of order. So because the plane is farther away from the surface of the Earth, its clock is going to tick faster. Just like the clock farther away from the black hole ticks faster. Remember that picture where as you get near the surface of the black hole, time slows down. The exact same thing happens on the Earth. The time of a clock will tick slower if you're on the surface than when you're in a plane. Not by much, but by a little. And relativity predicts that this clock is going to tick faster by 144 billionths of a second. It's 144 nanoseconds during the entire experiment when it flies around the world. But because it's moving so fast, much faster than the Earth clock, its clock isn't going to tick faster, it's going to tick slower by about 184 billionths of a second. When you combine these two together, you just add them together. The bottom line is, the theory of relativity says when you get in a plane and fly around the world, you should experience 40 nanoseconds less of time than everyone on the ground. So that means that it's predicting that you will have traveled 40 nanoseconds into the future, 40 billionths of a second into the future. So not much, but some future time travel. So they actually did this to see if this would happen. And they compared the clocks, just like in Back to the Future, when they compare the dog's clock and Doc Brown's clock, and they're ticking, and they're still ticking or whatever. And what happened? They measured within the experimental error something consistent with this. They measured that the plane went 59 plus or minus 10 billionths of a second into the future. So this was actually done in the 70s. Now, if you wanted to travel farther into the future, you would just need a plane that could go a lot faster, maybe a spaceship that could go a lot faster. We don't have the technology to do it, but the principle is there, and we've measured it. So forward time travel actually isn't science fiction unless you want to forward time travel a lot. If you want to go, a couple billionths of a second, we can do that as long as you can get on a plane that flies fast. Okay. And so, it would have been a little easier if they could have straightened the ground, but that would have been kind of dangerous inside that. Okay. So, it turns out this idea of time travel is something you all interact with every day, because there's these ideas that clocks tick faster farther from the Earth, and that clocks tick slower when something's moving faster than a clock on the Earth, are used and relied on by GPS. So every time you get out your phone to get directions, like I did when I was coming down here, you use this time travel effect. And let me explain how that works. This is just a really simplified view of how GPS works. GPS is a bunch of satellites going around the Earth. And what they do is they just tell everybody what time it is. So this one down here, this yellow one, just sits there and it's like, it's 4:59 and 50 seconds. It's 4:59 and 51 seconds. They just love to tell everybody all the time what time it is. And they just keep saying it. And there are a bunch of satellites. Here I'm just throwing 3. There are actually 24. I'm showing a red one, yellow one, and blue. So at the moment that I'm showing, they're all thinking to themselves, it's 4:59 and 58. Let's pick a time. And then 1 second later, they'll tell everybody, oh, now it's 59 seconds. Now, every time, periodically, but really often, so that it's basically continuously, these satellites don't just think this to themselves, but they broadcast a signal that's basically them yelling at everybody what time they think it is right now. They're the most important thing in the world. Because computers are dumb sometimes. And they're simple computers, and they're just telling everybody, hey, this is what time I think it is right now. So why would that matter? Well, let's see what would happen as we go to 5 o'clock. At 4:59 p.m. and 59 seconds, let's say this clock sends radio waves down to a receiver on Earth. And let's suppose that this thing is exactly 1 light second away. And 1 second later, the radio waves arrive. And so when my receiver says it's 5 o'clock, it also hears the yellow satellite say, oh, it's 4:59 and 59 where I am. And since you know how fast light moves, the receiver translates that into saying, oh, I'm 1 light second of distance away. And if you convert that into more familiar units, which it does, then it has a little translator chip in it, so it hears the yellow satellite saying, I'm 300 million meters away from you. Now, all the satellites are doing that. They're all saying. And so this satellite, my receiver, when I get out my phone, it says, oh, it's 5 o'clock. But then it also says, oh, I just heard the blue guy say it's 57 seconds, and the red guy say 55, and the yellow one say 59. And what you can do is then you can say, oh, I know how far away each of these satellites are, so you can triangulate and figure out where you are. Basically, you have to be somewhere on a circle that started at the satellites, and you know where the satellites are, because you can compute their orbits as a function of time. And your receiver has to be where all those circles intersect. And so you can do some math to say, oh, I know that each of these guys is saying how many light seconds away they are, or how many meters away they are, and you can use that to figure out where you are. And that's basically how GPS works. So when you get driving directions, this is what you're doing. Your phone is listening to all these satellites say, oh, this is what time I think it is, and then figuring out how far away they must be, and then combining that on a map to figure out where you must be. Now, here is a picture of all 24 of the GPS satellites. There's 24, so that at any given time you have at least 3 or 4 above you in the sky, so they're not blocked by the Earth. So no matter where you go, you can see them. There was something in the news recently about Russia threatening to turn off some utilities that we use to try to keep all the clocks synchronized on these satellites. So I'm kind of hoping that doesn't happen, because I get really lost without my GPS. I'm not sure if it would actually break the GPS as a whole, but it would make things inconvenient at least. But anyway, the goal of GPS, phone GPSs aren't so good, but the military has better GPS than we do, and they want an accuracy of about 2 meters. So how accurately must these satellites keep time? It's not enough for them to just tell you what time it is every second, because light moves too fast. If you want to be able to accurately get 2 meters, well, light travels 2 meters in just 7 billionths of a second, 7 nanoseconds. So for GPS to work, this clock, what they're really saying is 459, 59, and a whole bunch of the fractions, like 9 digits. That's what time I think it is. And then you do this triangulation to figure out where you are. But this is billionths of a second. That's the same size as the kinds of effects I was just telling you about by going up in an airplane and moving around the Earth. And these satellites are even higher up and moving even faster around the Earth. So it turns out GPS, it turns out the atomic clocks on these satellites have no problem keeping time to 9 digits of precision. That's easy. Well, maybe it's not easy, but they can do it. But the problem is the satellite clocks are higher and they're moving. And so both of those effects that were used by this plane that wanted to travel a few billionths of a second into the future also apply to these satellites on the same size as the precision of the time that we need to measure. So it turns out, if you were to ignore these time-traveling effects, GPS would not work. In less than a minute, the errors would build up to be bigger than 2 meters in your position. And the longer you ran the system, the worse it would get. So the next time your friend asks you for directions and you get out your phone, you should tell them this is using the theory of relativity to account for different rates of flow of time up in space and on Earth. It's a great way to make friends. All right. So that's forward time travel. And that's something that we really measure. Now, I want to finish the talk by talking about backward time travel. Backward time travel, I'm using a bit of a different background because this is something that's much more speculative. This is something I, like the forward time travel stuff, my research group doesn't really focus on, but I wanted to tell you a little bit about it anyway, because otherwise Haroon would have been annoyed with me. So here's what everybody really wants to know. Can the Back to the Future scenario happen? Can you go back in time and interfere with your own existence? That's the staple of all the sci-fi movies that talk about time travel. But there's a problem with this. And the problem is free will. Somehow something stops the hero, and the hero manages to prevent their own existence from being interfered with in some way. Like they just can't bring themselves to kill their grandparents, or they somehow, through some zany antics, manage to get their parents to fall back in love with them, or something like that. So there was a Russian physicist named Polchinski that had this idea. Let's explore this problem. Can you go back in time and contradict what happens in the future? But let's take all the free will physics out of it. Let's not argue about do we have free will or don't we. Let's just do this with billiard balls, just like the little particles you learn about if you take an intro physics class. So his idea was this. Can a billiard ball, you hit a ball on a pool table so it goes into a time machine, comes out back in time and collides with itself so it doesn't go back in time. So that's the same kind of a contradiction, except now there's no decision. The ball doesn't make a decision, it just does whatever the laws of physics say it will do. And that's the problem that Kip, my PhD advisor, and some students, well before my time, I was back in middle school back then, but they looked at this in a paper, and you can look this paper up online, and this is what I want to tell you about. The question is, can you have a billiard ball come in, go into a time machine over here, come out back in time over here, just early enough in time so they collide, and now it doesn't go into the time machine. Now it bounces over here instead. Can that happen? That's the question that they wanted to look at. And it turns out, aside from the fact that you've got a time machine, you can address this question using exactly the same physics that you learned in your very first physics class, intro mechanics. That tells you how to solve this problem, and they wrote a paper about it. So how does that work? Well, first let me just say a little bit about how you can make a time machine. So time machines rely on this idea called a wormhole. A wormhole is something where basically you can connect two different parts of space to each other. So how does this work? Well, let's suppose that we have two little spheres that are connected to each other, but we'll put one on a rocket so that its rate of time flows differently than the other one. So I'm plotting time going up. And so my brother's going to sit here on Earth and carry a clock. And so going forward in time, ignore this little cone here, his clock just ticks 1, 2, 3, 4, 5 as he goes up. Now if I fly in a rocket, my time will flow at a slower rate, and I'll travel into the future. So by the time I get back, his clock might say 8, and mine might say 5.5. Now if we're carrying a wormhole on the rocket as I come back, then, you know, let's say we're holding hands through the wormhole or something, although I don't like to think about that with my brother, then basically I could stick my head through the wormhole when I get back at 5 and see back in time where my brother was. So taking advantage of forward time travel, but if you could also have some tunnel through space-time that connects two places, then that's enough to do backwards time travel. So that's what I want to say about that. I'm going to skip some of these details for time. The one thing I wanted to mention was we're pretty sure this won't work. The problem is, in order to make one of these wormholes that could connect two parts of space-time, we're pretty sure you need negative mass to do it. We're pretty sure that doesn't exist. So we're pretty sure that that doesn't work. So I wanted to tell you about, so what? Let's suppose it does work. How would Newton's laws of physics behave with wormholes? Now it turns out I have a wormhole simulator on here that's going to take me a second to boot up. So I'm going to come back to the talk when that thing boots up, then I'll show you a little bit about how wormholes behave. So it turns out, I'll give you the bottom line, the laws of physics produce the exact same laws of physics that you learn from Newton's law. An object in motion is just going to keep moving in a straight line unless it goes through the time machine. And if it goes through the time machine, then kinetic energy is conserved, so it'll go in one side and come out the other side. And but it could change direction, like it might go in this way and come out pointing in a different direction. And then there's some rules about how collisions work when a ball collides with itself. If you take intro physics and do elastic collisions, that will tell you how they'll move. And basically one of two things will happen. Either this will happen, either they'll collide like this, and basically, and they'll look like this set of arrows where 1 and 2 collide, and then 1 goes out here and 2 goes out here, or you'll have something more like this. But the details of that aren't important. It's just that there are basically, intro physics will tell you how the balls will collide, and they'll tell you how you move through the time machine. And don't worry about these complicated diagrams. I just ripped these off from the paper. But as long as you know that the laws of physics will tell you what will happen, then you can just see how they behave. So I'm going to get out here and see if my wormhole simulator is working. Okay. So I don't have any internet, so I'm not sure if this is going to work. It sounds like it's good to go. Okay, so while I'm waiting for this to boot up, I could answer a couple of questions. Yes?
What makes time slow in a black hole?
What makes time slow when you get near a black hole? It's the curvature of space and time. Gravity curves space and time, and it turns out time is mixed together with space. So if the space gets distorted, the time gets distorted too. Yes?
If black holes are colliding and getting bigger and bigger, are they eventually just going to like take over?
Are they going to? That's a really great question. Are they going to eventually take over if that's all that's left? Yes, black holes will be the last thing left in the universe because they'll just keep colliding into bigger and bigger black holes and more stuff will fall into it. There we go. Okay, I'm going to start my wormhole simulator. Just for a second, I'm going to give you an idea of how wormholes behave. But I think I have time for one more question. Yeah.
What would the evidence provided that made Hawking lose the match?
That's a good question. I'm not sure of the specific evidence where he decided to concede, but some of the evidence was that we saw matter falling into a black hole, and it was heating up and glowing, just like when you put metal in a fire, it heats up and glows. And they knew it was falling into something, and they could use Newton's laws or Kepler's laws when they saw things orbiting around it to figure out how big it was, and they knew it had to be really, really massive. more massive than anything we know about, and yet totally black. So not emitting any light, so it's not a star. And so evidence like that, although I don't know specifically when he gave up. Okay, so I want to show you how wormholes work a little bit, so you know what to picture for this. So this isn't a time machine, but it's a wormhole. So let me go up here and show you how wormholes work. So the idea is you're connecting two parts of space together. So for instance, suppose I put a wormhole here and another one here. Then you can look through this one and see yourself looking out of the other one. I can take a block and I can carry it through. Things like that. Now, the important thing for this talk is what happens to an object flying through space when it goes through a wormhole. So I'm going to set up a little wormhole here for you. Drop it through. And now it's a projectile. Those of you who took intro physics, what shape did that follow? Parabola, exactly. So I will also follow a parabola if I go through this thing. And I'll show you one more thing. Not very practical, but I can make a gravity oscillator if I have wormholes. And I set this up just right. Yeah, there we go. So it's falling, but then when it falls through, it goes up the other side. So this is what I want you to picture when you think of wormholes. This is actually the most accurate wormhole simulator I know of. So let me come back to my talk. So given that, that's how objects behave when they pass through wormholes. They fall in and they come out at the same speed. If the wormhole is oriented in some way, they'll come out in a different direction. Just like I dropped that block and it was going straight down, but then it flew out the wall in a parabola. All right. So I was going to ask you a question, but I have a feeling I'm running a little bit over time. So instead, I just want to talk about this. I'll just take a quick poll. The question is, suppose I have a time machine, and I hit a billiard ball towards it. The question is, which of these is going to happen? So I'll just take a poll. Raise your hand if you think that A looks plausible. The ball will just go right through, and nothing weird happens. Okay. A few people kind of. How about B? Who thinks this is going to happen? The ball's going to go in, collide with itself, and continue on its way. Anybody think C, that we can't tell? Any of you have no idea, just want to take a guess? Okay, that's cool too. So it turns out the answer here is C. Newton's laws of physics say can't tell which of these will happen. Normally when you're in physics class and you get a problem, here's a ball and here's its initial position and velocity, you can solve that to know how it moves. But once you introduce time machines, there are multiple solutions. And how do you know which happens? Well, the laws of physics, at least if you don't, the laws of physics here, Newton's laws of physics plus time machines, just can't tell you. You don't know. So it turns out the problem isn't with backwards time travel, even assuming you have negative mass that makes the wormholes work. The problem isn't that you create these contradictions, like you go back in time and prevent their existence. The problem is there are too many possible outcomes that satisfy the laws of physics, and you have no idea which one would really happen. So it's a little bit different than what you would think. So they tried looking for contradictory cases. And let me show you what happened. Here's another case. They took a time machine like this. So when you go in and out, you come out and out one back in time. And they said, what do Newton's laws of motion say will happen? Well, one thing that might happen is it might just go straight through. Another thing that might happen is it might go, collide, get knocked into the time machine, come out, and then collide with itself and go back out. But another thing that might happen is it might go, collide, go into the time machine, come out, go back into the time machine, and then collide with itself. The third thing that might happen is it might go, have a collision that knocks it into the time machine, come out, go back into the time machine, come out, go back into the time machine again, and then collide with itself to start the whole thing. So Newton's laws of physics say all of these happen. So that's what I wanted to leave you with. So gravitational waves are something that we're really interested in because they're going to open a new window on the universe. We're going to see things like black holes smashing into each other. Time travel, forward time travel, not only is possible, but it's been done, at least a little bit. Forward time travel by centuries, well, that's still science fiction. Backwards time travel, we're pretty sure it's impossible because we can't make these wormholes that connect different regions of space. But even if you could, and they behave the way they do in this game Portal, which is how we think they really would behave, you don't get paradoxes. You don't interfere with your existence. Instead, there's multiple things that could happen that all satisfy. So I'd be happy, I don't know, I don't see a clock, but I'd be happy to answer any questions now or just afterwards. So thank you very much for the invitation.